All right, lecture 11C, seafloor mining. So we can consider three kinds of deposits on the seafloor that are being considered for metal mining. So we'll talk about them in order: manganese nodules, manganese crusts, and seafloor massive sulfides. And I'm going to introduce one which is sort of a subset of manganese crusts, which we might consider a new type. And the graphic there is not great, but it basically shows the three types: hydrothermal vents in the middle, ferromanganese crusts on the sides of seamounts, and polymetallic nodules on the deep sea floor. And really they're shown as separate entities, but they can all, you can find the same materials in close proximity in some circumstances. Okay, what's going on here? There we go. So deep sea mining. So we're looking at the world's oceans. And what you can see on this graphic is in the blue shaded areas are the areas of manganese nodules. So you see in the center of the image, there's the CCZ, which is the Clarion-Clipperton zone. That's sort of the main area that is of interest to explorationists in terms of manganese nodules. But you can see manganese nodules all over the place. The shaded brown, which is with the biggest one being the PCZ, which is the prime crust zone. That's the zone of manganese crusts. And then the dots represent seafloor massive sulfide systems that have been discovered to date. You'll see a lot of them concentrated on mid-ocean ridges, such as in the Pacific, East Pacific Rise or the Mid-Atlantic Ridge. But there's also some associated with arcs and back arcs, particularly in the Western Pacific and south of Japan, in the Izubonin Mariana Arc. And then, so why are we interested in them? So I've just picked out a few commodities. And so the first is the SMS, or the seafloor massive sulfides, then the nodules, and then what they call cobalt-rich crusts, which are just the manganese crusts. And so we can see that the SMS deposits are rich in copper, but poor in cobalt, whereas manganese nodules have reasonable copper and cobalt, and the cobalt-rich crusts have low copper, but lots of cobalt. And we look at gold and silver. The SMS deposits are much richer in gold and silver than the nodules or crusts. And then if we go across and look at the rare earth elements plus yttrium, we see that seafloor massive sulfides have very low rare earths. That's because rare earths don't substitute into sulfide mineral structures. Whereas for the crusts and nodules, those are very rare earth element rich. So good targets for the rare earth elements. Okay, so we'll start with manganese nodules, and they're sedimentary type deposits. And so these are mineral concretions on the seafloor formed of concentric layers of iron and manganese hydroxides around a core. And the core could be a shark's tooth, something, a shell, or something like that. And so they're found in vast quantities and contain lots of valuable metals, which we just discussed. And the cartoon just shows how they form. They form hydrogenetically or diagenetically. So hydrogenetically means from seawater. And so there's manganese and iron in seawater, forms oxyhydroxides, which settle to the seafloor, coalesce around these, the shark's tooth or shell or whatever happens to be at the core. And in doing so, manganese and iron oxyhydroxides have lots of reactive surfaces, and so metals can absorb to them and get incorporated into the nodule. Or they can form passively from seawater or from diagenetic fluids from below the sediment water interface. And so the image on the left shows a very dense field of manganese nodules. So you can see they're basically softball-sized things. And again, the map showing where these are. And so there's enormous tonnage of metal. None are being mined at the present time. So they're in 4,000 to 6,000 meters water depth, so logistically challenging. And there are concerns related to environmental which I'm not going to go into huge detail, but people who are pro mining the nodules would say that the biomass is small on in these deep ocean basins. The reality is there is lots of bio there. It's just more widely dispersed. So here's a picture of nodules cut in half. So you can see there might be something at the core, and then commonly they form sort of concentrically or semi-concentrically around that core. There can be dendritic growth as well. It just depends on the growth regime. So again, cartoon on the left just shows them showing hydrogenetic versus diagenetic growth from above and from below. And then the image on the right is just one of these cut in half. And again, you can see this concentric zonation as things accumulate, presumably punctuated in time, not continuously, would be my guess. And so how would they be mined? So the idea would be you'd have some kind of excavator, and the advantage of the nodules is they're right at the sea surface. So in terms of disturbance compared to on-land mining, relatively benign, except that there is life down there. And again, the proponents would argue that the relative amount of biomass is small compared to the disturbance on land. But the research there's still a lot of research that needs to be done in terms of the environmental consequences. But the idea is you'd have an excavator that would scoop up the manganese nodules along with associated sediment. Some of the sediment would be expelled out of the back of the excavator to form a sediment plume. Then the nodules plus water plus residual sediment gets taken up into a device that's going to pump it up the riser pipe to a surface ship, and the surface ship would then extract the manganese nodules and then pump down the residual sediment down to some depth below 1,000 meters to disperse the sediment plume. And so there's some concern about the sediment plumes. Some research has suggested that these sediment plumes would liberate toxic metals, but other researchers said no, it doesn't do that. So the jury is out because not enough work is being done. So they form very slowly, and the image on the left is a classification diagram. And so this is just some real data from a paper by Nozaki et al. Last year, and they measured this manganese nodule, and they looked at different layers within the nodule. So those red dots represent all their geochemical analyses within that nodule. And so it's a hydrogenous one. So it's formed at the seafloor, primarily from seawater. And as such, we can look at the rare earth elements profile. So we've talked about the rare earth elements and how important they are. In this case, the rare earth elements are normalized to shale, basically upper crust, just as a way of looking at the profiles. And what we can see, what's characteristic of these manganese nodules, is this very large positive anomaly over the element cerium. And this is because cerium is not stable in seawater. It converts to, all of the rare earths are in 3+ state, except cerium in seawater, where it's oxidizing, is in 4+ state, and it precipitates preferentially. And so the nodules preferentially incorporates cerium. So we get this characteristic pattern. And then notice this negative anomaly at yttrium. So we'll come back to a different look at this subsequently.
Hey, Matt.
Yeah.
What's interesting about that rare earth pattern, one of the issues of rare earth mining on land is the relative abundance of the lights compared to the heavies. And what you see here is there's a lot of more heavies relative to the light rare earth elements. Mm-hmm. And it's the heavy rare earth elements that have most of the value, not the light rare earths, although
that's true.
Although they're valuable too. But that is an interesting feature of these kinds of deposits.
Yeah. So this is from the same paper, and what they did was they looked at osmium isotopes. And the shaded or lighter symbols represent construction of osmium isotopes in seawater through time over the last 70 million years. And so there's this being progressive increase in osmium isotope ratio. Strontium isotopes have done the same thing. Thallium isotopes have done the same thing, perhaps related to global tectonic cycles, uplift of the Himalayas and that sort of thing. Yeah, Bob.
So the thing that you may not understand is that this is a single nodule and these are
Yes.
layers.
That's right.
So you've got evidence that at least one nodule took 35 million years to form.
Yeah, so they grow at the rate of 1 to 10 millimeters per million years. And so a lot of the nodules on the seafloor are on the order of 60 million years old. This was a very recent paper, and I happen to like the use of osmium isotopes. But yes, all those red dots are from the single nodule, which they broke into 3 layers and then took multiple samples from each layer. And so then they fit their osmium isotope values to the seawater curve. And in so doing, we're able to date the nodule to 35 million years.
Could it be a candidate for the oldest living organism on the planet?
The oldest living organism. Yeah, that's a good one. Well, the crocs are pretty old, aren't they?
30,
Yeah.
30 million years old? Because they're still growing, right? They
These
don't
are still
stop,
growing.
They don't stop growing until they get buried, and even then, not sure. As long as they stay on the seafloor, they'll still grow at whatever they grow at.
But the other thing I find interesting is this big gap, right? So there's what is that? More than a 10 million year gap of growth, which is interesting.
Mm-hmm.
So manganese nodules, so there's 4 main areas where manganese nodules occur. So the Clarion-Clipperton Zone, Peru Basin, Indian Ocean, and the Cook Islands. And I've just highlighted some of the key elements. So very rich in cobalt, very rich in copper, very rich in nickel. And total rare earths are pretty decent too. And it talks about the growth of manganese nodules. So it's pretty interesting. It's interrupted by ads, but it's still pretty interesting.
Deep underwater, 4 kilometers down, beyond the reach of our star's light, lie these dark, potato-shaped nodules. They've been there for millions of years, slowly growing in size, and these oddly shaped bulbs may hold the key to an electric future. We have known about these formations for over 150 years. In 1873, HMS Challenger even managed to collect samples from the mysterious abyss of the Midnight Zone, dropping kilometer-long hemp ropes with a collecting apparatus attached and by chance pulling one of these nodules to the surface. Each of these lumps contain metals that can help solve one of modern day's greatest supply chain issues: battery production, containing manganese, cobalt, nickel, and copper, and they are scattered all over the vast seafloor. It is estimated that a patch of land just over the size of Ireland can yield over 54 million tons of metals, collectively worth over $20 billion. Since their discovery, they've served as no more than interesting seafloor features, given that the precious metal they contain can be mined on land. There has been no incentive to profit off mining the nodules. But with growing supply chain woes and growing competition in the electric vehicle market, dozens of companies now seek innovative ways to surface these nodules. We know frighteningly little about the deep sea floor. As you descend past 1,000 meters, all light disappears, and thus so does all photosynthesis. The only light that may be visible is the faint twinkling of bioluminescence. Without sunlight, food becomes extremely scarce and animals rely on what is called marine snow, the falling debris of organic material from shallower waters. Because of these extreme conditions, the creatures in deep water have evolved to be some of the most unique in the animal kingdom. At 4,000 meters, you may find a semi-translucent Dumbo octopus scuttling along, or gulper eels with massive expandable gullets, or a viperfish with its terrifying dead eyes and unbelievably sharp teeth. Deeper still, scavengers and detrivores scramble across the bottom, looking for any morsel of food they can find. Animals like this have been found as deep as 11,000 meters at the bottom of the deepest parts of ocean. ROVs and some manned missions are beginning to scratch the surface, exploring the depths of the sea, but it is no easy feat. Only 4 crewed missions have ever been to the bottom of the Mariana Trench, the deep sea being one of the last ecosystems on this Earth that has been largely untouched by humans. This raises major concerns for the impact any mining operation will have on the strange and wonderful life residing among these metal-rich deposits. Early investigations of the seafloor in the 1960s and 70s revealed that the nodules are clustered in certain areas of the seafloor. Their locations depend highly on environmental factors, needing high oxygenation levels and a source of metal in the seawater or seabed to grow. Similar to how iron in steel reacts with oxygen and water to create a layer of rust, nodules are formed in layers of oxidized metal. For a nodule to form, a piece of debris has to sink into the oxygen-rich environment of the deep sea floor. From above, free-flowing iron and manganese ions dissolved in water react with the oxygen and form layers. These form nodules at the surface of the seafloor. From below, the metals get pushed up by concentration gradients through the porous sediment, and once they reach the oxygen-rich environment, they react and start forming nodules 10 to 15 centimeters below the surface. Depending on their depth, different percentages of metal will be present. While the majority of the metals in the nodules are manganese and iron, surface nodules are exposed to more cobalt, while deeper nodules collect more lithium and nickel. These layers form at astonishingly low rates, around 1 to 10 millimeters per million years. In the time it took our ancestors to spread out from Africa and dominate the world, these nodules only grew the width of a human hair. Scientists can predict where these nodules would appear based on these environmental effects, and we have confirmed that they appear in higher concentrations in the Pacific and Indian Oceans. Most of these zones fall under international waters, so the UN set up the International Seabed Authority in 1994, based in Kingston, Jamaica, to organize and control all mineral-related activities related to the seabed. Up to now, they have not granted any licenses for mining operations, but they have granted permission to a total of 19 exploratory missions of these polymetallic nodules, of which 16 are based in the Clarion-Clipperton Zone, or CCZ, an area just off the coast of Mexico. Each of these missions cover an area of about 75,000 square kilometers, approximately 0.16% of the area of the CCZ. Estimations for the potential yield of a mine this large are expected to be about 1.5 million tons of wet nodules per year. A typical electric battery has 35 kilograms of nickel, 20 kilograms of manganese, and 14 kilograms of cobalt. A mine this large would provide enough nickel for 400,000 car batteries, enough manganese for 18 million, and enough cobalt for 100,000 cars per year. The value of these deposits is undeniable, but we've never extracted solid minerals at scale from the seafloor before. This is going to require new technologies, and unsurprisingly, many borrow from the oil and gas industry, who are all too familiar with extracting value from the deep sea. Companies first have to locate a region where the density of these nodules is large enough to make extraction worthwhile. Autonomous submarines are first sent down to assess the area, using pulses of sound to scan and map the seafloor. The resolution of these scanners is too low to directly detect individual nodules, which are usually about 10 centimeters in size, but they can estimate the density of the nodules on the seafloor before sending down another expedition to collect physical samples. Now comes the difficult part: extraction. Many different solutions have been proposed, and there are several problems to overcome. Some trials were conducted in the 1970s and 80s, and the knowledge gained in these trials all led to the same proposals for a mining method. A self-propelled rover would be lowered to the seafloor, attached to a surface ship through a rigid riser and a flexible pipe. These risers are technologies created by the oil and gas industry and are well developed. Once the collecting rover touches down on the seafloor, it can move around, remotely operated from above. The rover effectively acts like a potato harvester, but instead of combing through the soil, most rovers use a water jet to dislodge the nodules and push them into the collector. Now, we need a way to transport the material to the surface, and this is where most of the technological issues are found. Once the nodules are dislodged, the collectors carry the sludge and nodules through a separator. The unwanted liquid gets expelled behind the collector, causing a plume of dirt to trail behind the rover. The leftover slurry with debris and nodules are now pumped up. Things get a little difficult here. Raising material over a distance this large requires a great deal of energy. However, attaching some kind of rope to raise material isn't easily scaled. Pumping liquid oil is vastly easier than transporting solid materials. Currently, two main mechanisms have been proposed to bring the nodules up to the surface. One way is to pump compressed air into the pipe, which creates the necessary pressure underneath the raw material to lift it to the surface. However, this method has a very low energy efficiency at about 15%. The second option is to space out submersible centrifugal pumps along the rigid riser. This is currently the preferred method. Once at the surface, the nodules are separated from the leftover slurry. They are then dried out for transport to the mainland. However, the unwanted slurry that is left over needs to be piped down and expelled into the water column. This slurry is one of the primary environmental concerns of deep-sea mining operations. Releasing at the top of the water column, where it can affect multiple levels of the ocean ecosystem, is not an option. At the very least, we need to pump the sediment down beyond the photic and dysphotic zones. These are the layers of the ocean that sunlight can reach. Pumping sun-blocking sediment above these layers would interfere with plankton and other photosynthetic organisms. An MIT study published last year investigated the dynamics of this sedimentation for both midwater dispersal and for the sediment dispersed by the harvester rovers. They found their models lined up closely with in-field experiments where they released sediment in exactly the same way off the coast of California. They found, thanks to the rapid dilution in the sea currents, that the sedimentation rate on the sea floor was drastically lower than normal background sedimentation, and thus should not interfere with filter feeders in the region. There was also no evidence of toxic elements in this extracted sediment. While it's tempting to compare this sediment to the toxic tailing pools we see in traditional ore extraction, these toxic waters are a byproduct of the ore processing. This part of the process does not happen at sea. This is simply surface sediment being returned to the sea. However, even if the plumes of waste product have minimal impact, mining operations have the potential to wipe out species we haven't even begun to study. Sea sponges use the nodules as anchor points, deep-sea octopus use them to lay and protect their eggs. And with these nodules taking millions of years to form, any surviving members of the species that depend on them would be left without a home, devastating an entire ecosystem which we have very little knowledge about, or its impact on the rest of the water column ecosystem. One of the few studies on the impact of these operations was conducted in the late 80s by a German government-funded research expedition off the coast of Peru. To assess the effects of nodule collection, they carved out trenches and removed nodules from an area 2 nautical miles in diameter. The first seabed disturbances were created in 1989, and after 33 years, the seabed floor has not recovered. The track can still be seen to this day. Filter feeders that depended on suspended food had a significant decrease in population, and affected areas showed lower biodiversity than controlled areas. Studies in other sites like the CCZ have also found a significant loss of life, up to 20% when compared to controlled areas. However, the sad truth is that the alternative is to mine these materials on land, which itself comes with environmental impacts. The vast majority of cobalt deposits lay under the lush forests of the Congo. To collect these metals, roads need to be built and forests need to be cut down. Another study compared the total emissions of both land and sea-based extraction methods and concluded that deep-sea mining of these nodules could reduce emissions by 80% for nickel, 76% for copper, 29% for cobalt, and 22% for manganese. These reductions are primarily driven by how these nodules are naturally occurring on the surface of the seabed, making extraction relatively low energy, and by the fact that ships are incredibly efficient at transporting loads. We also need to be incredibly conscious of the impending climate crisis. Ocean temperatures are rising, and with more and more carbon being absorbed into the oceans, they are slowly becoming acidic, killing off entire coral reefs. We need to transition to renewable energy as soon as possible, and these metals would accelerate this process. And there lies the dilemma that we, as the human race, have to ponder. Where do we collect the materials necessary to make a greener future? Is potentially destroying an unknown ecological system worth it to save the ones we know for a fact are in decline? Is it easier to find a new source of metals than to fix the problems with land-based mining? These are the questions we need to answer before exploiting this valuable resource in the deep, dark depths of our oceans. Climate change is the greatest challenge facing our planet, and we need more talented engineers and scientists working to solve this problem. That's why I talk about it so much on this channel, and why partnering with Brilliant to help educate the engineers of the future makes so much sense. We created our own real engineering themed course that you can take for free by signing up for their free trial. And if you found value in the math and science courses you took for free, and I'm sure you will, you can continue on with 20% off the annual premium subscription. Our in-depth interactive course teaches you about the physics of orbit and traditional rocket launches, before teaching you the fundamentals of kinetic launch systems, a course designed to help you understand spin launch, the subject of our recent documentary. You can get access to that course right now and all of Brilliant's other curated interactive courses by clicking the link in the description. One of my favorite courses on Brilliant is programming with Python. Python is a versatile coding language and a fantastic first coding language to learn. It can be used for everything from video games to data visualization to machine learning. I used it to code custom scripts for engineering software for my master's thesis. I wish I had Brilliant back then to teach me the basics and to guide my learning, instead of trawling through textbooks. Brilliant teaches Python with interesting and fun interactive courses that challenge you along the way, making the learning process much easier and more rewarding. And they're adding content monthly, so there's always something new to learn. You can get started for free by clicking the link on screen now, and the first 500 people to do so will get 20% off Brilliant's annual premium subscription.
Not going to show, but the link is there. And it talks about the growth of manganese nodules. So it's pretty interesting. It's interrupted by ads, but it's still pretty interesting. Nope, don't want that. And then this is another video. It's only a few minutes long, but again, I won't show it because it's kind of a promotion. It becomes promotional, but this is the metals company is a company based in Canada, and their whole shtick is mining the seafloor. And they're actually working with the United States government right now because the U.S. government is very interested in mining the seafloor. And as we'll talk about, the U.S. is not a signatory to the International Seabed Authority. So it's a question of who gets to decide where to mine.
The White House is deciding whether to permit a first-of-its-kind mining project at the bottom of the Pacific Ocean. Now, it follows an executive order signed by President Trump. This is way back in April, aimed at jump-starting the deep-sea mining industry. Spearheading these efforts, the metals company. Its shares have, in fact, soared more than 75% since the executive order was signed. The company aims to mine minerals critical for batteries and other green technologies from the Clarion-Clipperton Zone. Now, this is where it gets interesting. It's part of the Pacific Ocean with potentially billions of dollars worth of minerals Critics, though, warn that doing so could cause irreparable environmental damage. Gerard Barron is the CEO of the metals company, and he joins us now. And I thank you for taking another crack at this. We had breaking news the last time we tried to interview, so thank you for having us back. And I do want you to give us a primer on this, on what your company is trying to do, and why you believe it is both necessary and achievable, keeping an eye on the fact that many are skeptical that this is needed and that environmentally it won't be dangerous.
Thanks, Paula. Well, so we're focused on picking up these polymetallic nodules from the abyssal plains in the Pacific Ocean. And if we think about our planet, 70% of it is known to be covered by the oceans. And we don't take any metals from the oceans today. And so it makes sense, if we apply first principle thinking, that we should carry out extractive industries in parts of the planet where there is the least life instead of the most life. And if we look at what's happening on land today, we're continuing to push into some of the most pristine, biodiverse habitats known as our tropical rainforest. Yet we have trillions and trillions of dollars worth of these polymetallic nodules. It's estimated there's more than 20 billion tons of them. And they're full of nickel and copper and cobalt and manganese, and they sit in the abyssal plains. Now, half of our entire planet is categorized as the abyssal plain. There's no alternative use for it. You can't grow crops there, you can't live there, and there's no one living within 1,000 miles of it. So it's the perfect place to have a very large, abundant resource. And the metals company, for the last 14 years, has been focused on carrying out the environmental studies to understand what the impacts will be of us picking up these rocks and turning them into metals. And in 2022, we ran commercial trials where we showed how we pick up these rocks using our robots on the seafloor. We also did extensive environmental studies during those campaigns, and then we went back a year later to see what the recoveries were like. And the good news is the recoveries are really fast, and the rocks literally sit on the ocean floor. So we don't have to drill or dig to get to them. We just have to pick them up. And we all know the geopolitics at the moment are very focused on critical minerals. And so it's a given that we need to get more of them. And it only makes sense that we should be going to the abyssal plains in the middle of the Pacific Ocean to pick up these rocks.
Certainly it makes sense to you. I would say that if we want to just deal with the technology and the timelines first, this is still very unproven. Why do you believe it will succeed, and why do you believe it will succeed in a timely fashion? I mean, 10 years ago, there's a lot of technology we couldn't see coming. If it's going to take you 10, 15, 20-year timeline, what's proven about this, and why is it even worthwhile?
Well, if we go back to the 1970s, this industry almost got started. America was leading the industry, and there were many consortia picking up these very same rocks. And in the 1970s, they were real pioneers. And so, of course, the industry then came to a slowdown, and it's only now, since the metals company has really been pushing the industry forward since 2011. And in 2022, we went and showed how technology has advanced, because of course what's happened in that 50-year period is offshore oil and gas and pipeline and cable laying has advanced enormously. So it's more about technology integration, to be honest. And so there's no big technology risk in picking them up. And of course, we've also shown how we move them to shore and turn them into the critical minerals that are inside them. We've done all of that pilot work now. And to begin with, there are existing processing plants that we can utilize to process these nodules. But of course, the big opportunity is to rebuild that infrastructure in the United States. And of course, President Trump is very focused on reindustrialization. And there's a great saying, if it ain't grown, it's mined. And so critical minerals are going to be needed. And we're going to need billions of tons more of them. And the question for society is, where should we be getting them from? And surely we should be getting them from places where the impacts on people and the environment is less.
And Mr. Barron, to that point, I do want to say that the president is actually in the Oval Office right now. He is supposed to be signing an executive order that will actually make investment in that energy infrastructure much simpler. Still, though, so many people are wondering what the cost will be of this from an environmental point of view, given all the damage we've already done as you know, on land, never mind at sea. And I ask you that I believe that, you know, so much of what you're about to mine is kind of beyond national jurisdiction, right? It's in international waters. You know, the International Seabed Authority, the ISA, has been abandoned by the Trump administration, and apparently it's not something that you're going to adhere to either. But and please correct me if I'm wrong about that.
No, we were working with the International Seabed Authority. It was set up in 1994 with the express purpose of putting in place regulations to allow the exploration and extraction, mining of these metals. Now, of course, they haven't delivered on that promise. And so in March, we announced that we were going to go through the permitting pathway of the United States. And of course, no nation has sovereignty over the oceans. And so all nations have access to the minerals on the seafloor. They have freedom of passage. They have the ability to lay cables. A number of nations, in fact, now 169 of them, did sign the treaty, now known as UNCLOS, that agreed on how they would handle minerals that lay on the seafloor. But America did not sign. In fact, it's been a consistent objector to that treaty. And so America has full legal right to be able to go and collect these metals.
So
they also have the regulations.
And we do understand that that's the direction that President Trump wants to go in. I do have to leave it there. Gerard Barron, we'll continue to check in, though, with your company. Appreciate it.
Thanks, Paula.
Okay.
The White House is...
All right, so now we're going to move to manganese crusts. And these are also sediments. Right? So they're also referred...
Was that a question?
What's that?
Oh, was that a question by someone?
I didn't see one. No, that was the video.
Righto.
Okay. So just on the right, just some images of some of these manganese crusts. So they're also referred to as cobalt crusts because they are rich in cobalt. They're metallic, so they're iron and manganese oxyhydroxide layers. They form on the flanks of submarine volcanoes or seamounts. Again, they're very slow growing, actually maybe slower than the manganese nodules, sort of 1 to 5 millimeters per million years. But they can be up to 25 centimeters thick. So they can reach pretty interesting thicknesses over very long periods of growth. So this is a map of where manganese crusts are. So the blue areas are the nodules, but the orange are the manganese crusts, or the cobalt crusts. So again, the main area here is just to the east of the Isubone and Mariana Arc. But they're all over the place. Interestingly, there's none indicated in the back arc to the Mariana Arc, and we're going to talk about those subsequently. So what are they rich in? Well, so this is an interesting table. So the first column is the cobalt crusts in that PCZ, the prime crust zone, just east of Japan. The second column is global reserves on land, which are economically mineable. The third column is global reserves on land that are economic and subeconomic. And then the fourth one is manganese nodules in the Clarion-Clipperton zone. And so again, I've just highlighted a few things. So the rare earth elements, the PCZ, these are in millions of tons. So 16 million tons versus 110 or 150 on land versus 15 in the Clarion-Clipperton. So smaller than on land, but still significant and perhaps more easily extractable. Nickel. So the Clarion-Clipperton, the nodules are very rich in nickel. Cobalt. So these crusts contain more cobalt than deposits that are known on land. Yttrium are higher than on land, and thallium much, much higher than on land. So very rich sources of metals. And this plot just shows the difference between crusts and nodules. So the crusts have lower manganese but higher iron than the nodules on average. They have higher cobalt but lower nickel. higher rare earth elements and lead, but lower copper and zinc. So these would be different targets for different commodities.
So, Matt, there must be, microbes doing this work, right? And somehow the microbial connection is what's going on here. And we don't talk much about that, but obviously
yes.
the science in that is moving in that direction. So Madison may have a comment about that.
Yes, I confess, microbial stuff is not my forte.
I would say it's really interesting. It's just really challenging to study anything that grows that slowly in the lab, especially in the time span of, say, a graduate student.
You don't spend 1,000,000 years in the lab?
It feels like it.
Yeah, I've had some students where it feels like it to me too. Okay, moving on. So how do these manganese crusts form? And it's quite interesting. So they form on seamounts. So here's a cartoon of a seamount. And in the oceans, there's this thing called the oxygen minimum zone, which is typically around about 1,000 meters deep. And that occurs because of falling organic matter. Organic matter from the surface layers falls down and it gets consumed and converted into dissolved inorganic carbon. And so that requires oxygen. And so oxygen gets consumed. And because it's a low oxygen zone, there's less formation of iron and manganese oxides. And so metals can accumulate in the water column. So then we have deep oxygen-rich water comes up along and upwells against these seamounts and mixes with this oxygen poor water. And so oxygen poor, not poor waters. And so then we get precipitation of iron and manganese, and the metals absorb to those iron and manganese oxides. So it's very cool.
So presumably over 30 or 60 million years, that mixing zone is going to move up and down depending on the amount of oxygen-rich deep water, which is glacially related. So
that's right. That's right.
Right. The question might be, with more oxygen-rich water than we've had for most of Earth history, are the nodules and crusts growing faster now or slower?
Yeah, that's a good question. And if we can even recognize them in the ancient rock record. Yeah. There's just a pretty picture of a very thick manganese iron crust. Okay, so now we're going to switch gears, and maybe this is a fourth type. So the map on the right shows the Mariana Arc, and so you can see the Mariana Trench in the purples and blues, or sorry, purples and deep reds, and then the arc is expressed by the line of volcanoes, and some are subaerial and most are subaqueous. You can see them going here, and behind that we have the Mariana Trough, which is the back arc to the Mariana Arc. And the symbols refer to manganese crusts that are being sampled by Hein et al. In the northern part, and then by a cruise that Bob Stern and I were on more years ago than we would care to admit. And
2001.
2001. I know. It feels like so long ago. But I'm going to show some data from these samples, which is hot off the presses. So these crusts, so we collected a bunch of manganese crusts in the back arc, or just behind the arc here, and they're hydrothermally influenced. And so what's interesting about them is they have lower metal loads than the ones we were just talking about, but they grow much faster. And so this is a chart. It's a little hard to see, so I just highlighted a few elements. This is from actually, I should have given the reference from a paper that a student of mine published with Bob and I a few years ago, 4 years ago. And so what the plot shows is the average composition of the crusts that we sampled versus hydrogenetic crusts, the average of hydrogenetic crusts. And so the ones that we sampled, these hydrothermal ones, are rich in lithium and cadmium relative to the other crusts, but copper, heavy rare earths, and cobalt, they're much less rich compared to the manganese crusts that we were just talking about. Here's some pictures, and what's hot off the press is you'll see the numbers to the right of each nodule, or each crust, sorry, they're not nodules, is age dating. So we recently did some carbon-14 dates, and to my knowledge, it's the first time anybody's dated one of these crusts by carbon-14. It's a little unclear. We've got ongoing work to see what we actually dated, but nevertheless, if we look at this one on the upper right, you can see that near the bottom is 1,300 years old, and near the top is 5,500 years old. And that's about a 6 centimeter thick crust. So that's on, that's on the order of centimeters per 1,000 years, which is 1,000 times faster than manganese nodules and the cobalt crusts. Yeah, Bob.
Okay, so this is kind of cool science. So when I saw these results, I said, Matt, something's wrong, because I assumed that these crusts grew from the inside out. That is, that the things that are at the bottom should be older than the things at the top.
Yeah.
And our co-author, Jim Hine, who's an expert on these things, says, oh no, these things grow from the bottom up. So, right now we're sort of struggling with this. But if these carbon dates have any value, and we certainly wouldn't have collected them if we didn't think they did, these things grow many orders of magnitude faster than these crusts in other environments. And if you're anything like me, when you first saw a crust, you went, oh, that's ugly, throw it overboard. But then Matt comes along and goes, wait, Bob. This stuff is interesting, and you can see what he's done with it is turn this into a really frontier kind of a study. So this is frontier science, and we're still at the exploratory stage. And Matt, you're revising this manuscript, and
I am, and I have someone who's doing detailed SEM work to determine. So we measure the inorganic carbon in these materials, not the organic carbon. And so she's trying to determine what is actually the host to the carbon in these layers. And so far, it looks like it's shells, so critters. And so presumably they deposited around the same time that the layers do. So I'm starting to think these numbers have validity. So anyway, it's pretty cool. It's very exciting. So I consider it much more of a renewable resource than the nodules, which take 60 million years to grow, right? So, and here's some rare earth element patterns from those same crusts that you just saw with the age dates on them. And these are from different layers. So the numbers aren't really, or the sample numbers aren't really important. But if you remember back to the nodules with the very high cerium anomaly, these ones have little to no cerium anomaly or a negative one. And then they have little to no or a positive yttrium anomaly. So they're quite different from the manganese nodules and the slow-growing manganese crusts. And these patterns are reflective of a hydrothermal influence. And then we saw earlier the same discrimination diagram. So this circle up here is hydrogenetic. This one here is diagenetic. And down here is hydrothermal. And this is just a cloud of data for some of these nodules, just showing that there's a fair extent of hydrothermal influence on these nodules. Okay, Oh, the last one.
So Matt,
Seafloor massive. Yeah. What was that?
oops, sorry.
That's all right.
Can you go back and show us how you infer hydrothermal versus hydrogenetic from
Right.
these diagrams?
So these diagrams, this was, I forget who made these diagrams. What they've done is just taken lots of data from diagenetic nodules, hydrogenetic nodules and crusts, and then hydrothermal deposits. And so the hydrothermal ones, as I mentioned before, are not as metal rich as the others. And so they plot towards the iron and manganese apex of the triangle. And what the data represent is a large cloud of laser ablation analyses that we did on individual crusts. And all it's really showing is that mostly these crusts vary between hydrogenetic and hydrothermal. So this one here is dominated by hydrothermal influences. Same with this one up here. This one here, the green one, is basically a mixture of hydrogenetic, diagenetic, and hydrothermal.
You know what's interesting about this is the hydrothermal ones, they're going to be around already polluted areas, right? A hydrothermal vent is basically nature's pollution. Now,
Yes.
there are critters that like that kind of pollution, and the pollution we would do mining them would definitely disturb them. But, you know, the deep ocean, the hydrogenetic environment is much slower, and you can see it because it's so much richer in things like zirconium, yttrium, cerium, rare earths. Those are telling you this is a hydrogenetic thing.
Yeah.
And then the diagenetic, that's quite controversial whether or not these things grow under the seafloor or not. Obviously, you can't take a photograph of it very easily. You have to interpret it. And if you think about how to mine these things, you know, mining around a active hydrothermal vent isn't going to cause any serious because that environment's going to rejuvenate itself very quickly. Mining a hydrogenetic or deposits nodules on the surface, that's going to cause a certain amount of disturbance of the substrate. But mining diagenetic nodules, if we should ever find such a deposit that's economic, would, you know, require really digging up the substrate.
Mm-hmm.
So these imply different environmental problems.
Indeed. And I'll speak to a little bit of that when we talk about Nautilus minerals. Okay, so finally, seafloor massive sulfide deposits, and these are hydrothermal. And so the cartoon here just shows the sort of different styles of formation of VMS deposits. So we call them SMS deposits when they're forming on the seafloor, and we call them VMS, or volcanogenic massive sulfides, when we mine them on land. And so we can see we've got on the left-hand number one here, we have a deep fault, we have a feeder zone, stockwork mineralization, we have a mound, we have hydrothermal venting, we've got some chemical sediments coming off to the side. Over on number two, we have perhaps a stratified ocean, and so things can form where it just is a different style of formation. And number three is more explosive. And number four is sub-seafloor mineralization. So there's no actual venting. And of course, it's a continuum between all of these. And it also shows seawater comes down, gets heated up by the magma source at depth. And so we get a hydrothermal circulation. And there may be influence of magmatic volatiles plus or minus metals as well. There's good evidence that that happens. So we've seen the image on the right we've seen before. That's sort of a classic mound, chimneys, and then a stockwork zone for a VMS deposit. And, you know, VMS deposits are on the scale of, you know, 500 meters in diameter, that sort of thing. They're not huge things. And so we could think back to what Bob was talking about, some of these near Earth objects, you know, on the scale of hundreds of meters in diameter to up to a kilometer in diameter. Those are big. right? When we compare that to a non-land deposit. The image on the left just shows the depth at which we find these seafloor massive sulfide systems. So the ones on the mid-ocean ridges are deep, and ones in the arcs are much more shallow. That's the basic take-home message there. So go back to this map.
Matt, if we could go back to follow up that comment. So a company going, oh, why would we invest in, whatever the capital required to mine one 100-meter body? Well, yes, but these tend to be concentrated in, along plate boundaries, which are very linear. So if you find one, chances are pretty good there's another one.
Exactly.
Not too far away. So you just, the infrastructure is on the boat. You would just pick it up. So it's a different style. It would be a different style of mining. You wouldn't go after a single deposit. You would be going after a family of deposits.
Yes, and I'll show that in a minute. Yeah, that's exactly right. So again, just showing the map of where these things occur. So the red colors are active. The yellow colors are unconfirmed if they're active or not. And just showing that the different environments, mid-ocean ridge, back arc versus arc or rifted arc. And this is kind of what we're looking for, these high temperature hydrothermal chimneys. So you can see the plume of quote unquote smoke. It's not smoke, it's iron sulfides being precipitated. And the temperature out of this orifice was measured at 302 degrees C, if I remember correctly. This is from Brothers Volcano on the Kermadec Arc. And so basically these things form by chimneys forming and then collapsing and coalescing into these mounds, and then subsea floor mineralization as well. And these chimneys are composed of pyrite, chalcopyrite, sphalerite primarily. So copper minerals, zinc minerals, and iron minerals, but a fair amount of gold in them too. And so how do we find them? Because, these things are small and the sea floor is vast. So we find them because that black smoke is rich in iron, methane, hydrogen sulfide, iron oxides, manganese, and helium. And so it's hard to find the vent. It's easy to find the plume. And so that's how we find them. We find the plume and we can vector, because these different chemical species, it's like a chromatography. They change with distance from the vent. And so we can vector back to where the vent is. And we do that by using something like this. It's called a CTDO. So it measures conductivity, temperature, depth, and optical properties. And then we have these bottles so we can collect water samples remotely. And you just drag it through the ocean, going up and down in a pattern like this in the bottom panel, up and down through the water column, and we measure things like the turbidity. That is how cloudy the water is. And when it gets cloudy, like here, that's a hydrothermal vent right there in a caldera. So that's how we find.
Just want to comment. They call this method the toyo, right? Because it's like a yo-yo in that it's up and down, but it's being towed, so they call it a toyo.
Yeah, so the ship drives at about a knot and a half, and then the package is just raised and lowered continuously. Some captains don't like doing that because they don't like things hanging off the back of them when they're driving the ship. But usually we had a German captain who wasn't too happy about it, but he gave in eventually.
Did you consider paying him?
No, we pay out the line. We don't pay the captain. And then once we've found them, we got to go explore them. So one way is a submersible. So this is the Japanese submersible Shinkai 6500. There's a diver going to help collect it. Or we use remotely operated vehicles. This is a Japanese one, the Hyper Dolphin.
Yep.
Or we use, what's that?
And I just wanted to point out for members that don't know that, Bob Stern actually got in that previous thing, the
Oh, this
Shinkai
one?
6500, right?
Yes, a couple of times, and Ignacio did too.
Yeah, I'm extremely jealous. I was on a cruise with Shinkai, but I didn't get to go in, which is too bad.
Yeah, it's crowded.
Yeah, yeah. Well, yeah, yes. And the other way we can help find them is using autonomous underwater vehicles. So this one, the AUV, has arms, and it's operated from the ship, but it has arms, so we can collect samples with it. The AUV is used for mapping and finding hydrothermal plumes and things like that. So these operate without a tether. So there's no line. You just throw them in the water, and they do a pre-programmed flight path, maybe 50 meters above the seafloor. Fantastic devices. So let's talk about an example. So there was a company called Nautilus Minerals, and they were formed in 2007. And they decided that they wanted to mine a seafloor massive sulfide deposit called Salwara 1, which is, here's Australia, here's Papua New Guinea. So the red box comes down to here. So we have Papua New Guinea, we have the island of New Britain, and there's a whole series of seafloor hydrothermal systems, all with different Salwara numbers. And Salwara 1 is right over here. And so that's it there, just off the coast of New Britain and New Ireland. And this is sort of showing the tectonic regime. So we have failed subduction that ceased to the north. And we have subduction to the south, which is north directed, which is active in the New Britain Trench. And so we have these pull-apart basins in the back arc. And that's where, so we're rifting the back arc, and that allows seawater to get down towards the magma source and then produce hydrothermal fluids. And so there's a whole series of these hydrothermal deposits along this back arc system. This is a more close-up, so you can see these square boxes where these are tenements that like staking on land. So it's staking on the sea floor. And so Nautilus staked, quote unquote, a bunch of these hydrothermal systems. Like different colors here just represent different rock types.
Who did they stake with?
The government of Papua New Guinea.
Okay, so this is in
This is in Papua
PNG's
waters.
territorial
Yeah.
waters.
That's right.
Okay.
That's right. And so they drilled. You drilled the deposit. So here's a cross section. This is Salwara 1, so it's not huge. I'm talking a couple hundred meters across, maybe 20 meters deep of sulfide mineralization. And yet they were very active and aggressive at potentially mining this. Hasn't happened, but there you go. And I should say that when they decided to if they ever mined it, they were going to leave, because as Bob mentioned earlier, there's these hydrothermal vent communities around these, because this is an active system. They were going to leave islands of hydrothermal communities separate to recolonize once they'd finished.
Now, Matt, you said they gone bankrupt.
Yeah, that's in a later slide, but yeah, they
Okay.
went belly up in 2019.
Okay.
Yep. So this is their seafloor drill. They just drop that down to the seafloor, and it has a remote operations, so it drills. And this is what it looks like on the deck of the ship. Here's some people looking at some of the core. There's the core barrels and the core. And this is some of the chimneys that they had at Salwara 1. So we can see the manipulator arms on an ROV, remotely operated vehicle, collecting chimney material. And here's some of the chimneys they collected. So on the left is a cross section of a chimney. So you can see the central orifices where the hydrothermal fluids would be venting upwards, going into the screen. And you can kind of see that central orifice over here. on this chimney. So again, dominated by pyrite, chalcopyrite in this one. So how are they going to mine it? Well, basically with excavators. And they would just go in and drill or scoop, basically benching, just like you would in an open pit mine, except they're not going very deep. And so you can see in this image, you've got these scoopers or these excavators just benching the deposit, sending that material up to the ship where they would take out the sulfides and put the sediment, remaining sediment, the leftover sediment, back down towards the seafloor. The idea being if you get the sediment deep enough, it wouldn't interact with much life in the water column. The chart on the top just shows their inferred and indicated reserves. So about 2.5 million tons at around 8% copper, 5 or 6 grams per ton gold, 20, 30 grams per ton silver, not very much zinc. And so contained copper in tons is about 200,000 tons of copper and about, 500 kilo ounces of gold, 500,000 ounces of gold. So they went bankrupt. They just didn't get the financing, and there was environmental concerns. But they were the closest ever that anybody's come to mining a seafloor massive sulfide system. And so we have to ask the question, is it worth mining seafloor massive sulfides? This is a plot put together by Al Galley in a paper, and I mentioned Windy Craggy in the previous lecture earlier this evening. So Windy Craggy is one of the largest VMSs in the world. Average VMS deposit is around 10 million tons, and a typical seafloor deposit is less than 1 million tons. So, are they worth mining? So here's a great tonnage model, and it's from Al Galley, but what I've put is a big star for where I think Solwara 1 is based on their data. So this upper plot shows copper plus zinc plus lead versus tonnage. And then the slanted lines then represent the amount of contained metal, i.e., in this case, the amount of zinc, copper, and lead. So over here, on this one here, if a deposit's, say here, it might be a 50 million ton deposit with 1 million tons of copper, lead, and zinc at 10% average grade. Okay. You can see some of the giant deposits in the world: Windy Craggy, Caribou, Kidd Creek, Brunswick 12, Flin Flon. These are all in Canada. They're all super giant deposits. So Solwara 1 is kind of middle of the pack. Here it is for gold. Again, it's sort of middle of the pack. The red box just represents seafloor massive sulfide deposits. So relatively small. I had a talk last Friday given by an expert on this, and he argued that no, they're not big enough to mine. However, as Bob said, they occur in clusters. And so if you can put together a bunch of them, maybe it would make sense.
Well, let's think about this a little bit more. So number one, it's 20 years to develop a mine because of the permitting. You've got these interactions with the local people, the environmental ugliness of a big waste pile, and you have to pay. Whereas these things, they're smaller, but it doesn't really, the size of the deposit doesn't matter. It's the economics of the project. So if you've got a much bigger mine deposit, but it takes you, much more money to develop it. Whereas on a ship, you just lower something, bring it up, go to port. All of your infrastructure is self-contained. It's really a question of what is the return on the investment. And it could be that a small to medium-sized deposit on the sea floor is worth it, especially keeping in mind what Astroforge is doing with asteroid mining, which is much less, I think, is less less immediate than seafloor mining. If you can show that you can do it at all, the value of your company goes up tremendously. So you wonder, what were the nature of the environmental concerns, and how do we move to an experiment where we do a mine and we also monitor the environmental consequences rather than talking about them.
Well, and I think that's what Solvara 1 was supposed to be, was a demo. Yes, they wanted to make money, but they wanted to show that you could do it. Like your asteroid mining company that just wants to show that it can be done. So the other consideration is that these are surface deposits. So the amount of waste rock compared to an open pit mine, the amount of waste rock is really small in a seafloor mine.
Yeah. So you really are curious, what were the environmental concerns? Yes, you're going to be disturbing the natural environment, but there's got to be trade-offs. And would we rather disturb the natural environment in a place where nobody lives, or in a place where, like in Guatemala, or some of the regions in Canada where you've got First Nations, and in the United States too, where you've got First Nations complaining that, of course, you're mining our most sacred site. That's going to cost you big time.
Yeah.
Whereas here, maybe a few fish are going to be disrupted. So this is really interesting. You wonder if it's too bad that Nautilus couldn't get to, actually generating some metal and getting the environmental consequences evaluated.
Yeah, go ahead, Clint.
Note to class, remember the way to make money in mining is sell shit to miners. Like, it's going to take specialty equipment. I mean, I'm not just talking about selling them blue jeans. I mean, to do this in this environment, which is a pretty harsh environment, the deeper you go, the more specialized the equipment is going to be.
Well, the interesting things.
Go ahead, Bob. No, you go ahead.
I just want to say that in general, these kinds of deposits are not in particularly deep parts of the ocean.
No, this one's about 1,600 meters.
So, the challenges increase exponentially as you go deeper and deeper, but 1,600 meters or so shouldn't be any particular technological challenge.
No, they actually had a ship built, and then it got sold to do something else. But yeah. Okay, so unlikely? Perhaps. But maybe. So my colleague who gave this talk on Friday, he didn't mention the systems that are just off axis of the Mid-Atlantic Ridge. So the Google Earth image with the star, that's where the Seminoff vent field is. So the images on the right, there's a topographic map of the Mid-Atlantic Ridge, and there's the Seminoff deposit or vent field here, and here is a cross section. And I'm just going to focus in on Seminoff 3 and 4. So 3 possibly could have as much as 40 million tons, and Seminoff 4, I've seen estimates of 40 million tons or greater than 100 million tons, which is what it says here. So the stuff that's on the axis tend to be quite small, but the ones that are off axis, they can exist for much longer periods. So Seminoff is on the order of, I think Seminoff 4 is on the order of 130,000 years old. So it's had a long time to accumulate a lot of metal because it's off axis, and we've got these fluids coming up, these basically these fault networks associated with rifting. And these are ultramafic hosted deposits. So they're not hosted in basalts, they're hosted in ultramafic rocks. So I'm just putting that out there as a thought experiment. Maybe there are some that are big enough to actually rival stuff that's mined on land. Yes, this would be in deeper water, but nevertheless.
But now the question is it better to mine in, in an area that is not claimed by any nation or to mine in an area that is, right?
That is
So
the question.
Papua New Guinea, all you have to do is get the approval of the Papua New Guinea government and all of your legal issues are taken care of. Whereas if you mine in the middle of the ocean where the law of the sea might pertain or might not, the lawyers are going to see the risk as being greater, I imagine.
Yes, undoubtedly. So, and that's a nice segue into who gets to decide. And so deposits that are within the exclusive economic zones, which is usually 200 nautical miles of individual countries, that's largely up to that jurisdiction. And some countries are permitting the exploration for seafloor minerals, including Japan, the Cook Islands, Papua New Guinea, and Norway has, although I think it's suspended this exploration. But many marine deposits are in international waters. And so the rules around seafloor mineral exploitation are decided by the International Seabed Authority, the ISA. So the ISA was formed by the United Nations in 1994 as part of the Convention on the Law of the Sea, which is commonly known as UNCLOS. And ISA has granted exploration licenses in international waters, 31 if I remember correctly, but no mining because they still have not formulated the regulations around deep sea mining in international waters. Interestingly, all the major countries with a coastline are signatories to the ISA and UNCLOS, but not the United States.
So that if the ISA has granted exploration licenses, but no mining licenses, because there are no regulations about seafloor mining, what is the prospect of ever getting any regulations?
Well, I guess that's going to, so you can imagine so I think China has the most of the licenses, I think 5, if I remember correctly, of any country. And you can imagine if a country big enough like United States or China did enough research and decided, yes, there's a resource here, they could put pressure on the UN and the ISA to come up with the regulations. Or, in the case of the United States, if they're not a signatory, they can just go ahead and do it anyway.
It might be a fun class project for some class, not this one, to write the regulations.
There you go.
That would be a very interesting exercise.
Yeah. Yeah.
I think Google doesn't have their first do no evil motto anymore. So since they're obviously committed to doing evil now, maybe we can use that.
Yeah. What's up, Clint?
Just this is another example of where, if departments ever work together, they could put together a hell of a good course that involved mining, business, and law. Yes. But that's going to happen in fairyland, but not here.
Okay, I'm going to finish off with, so November 1st was actually International Day of the Deep Seabed. Who knew? I didn't until this morning. And so the Secretary General of the United Nations had this, this is just a quote from her press release. So the deep seabed is one of Earth's last great frontiers. It's home to geological formations and ecosystems millions of years in the making. One can argue the nuances of that. Ecosystems that advances in technology and innovation are helping us to better understand. Geological processes have led to rich mineral resources that are of interest to human pursuits, but its value is far greater than minerals alone. It's a place of discovery and wonder and blah, blah, blah. But the frontier belongs not just to us, but to generations to come. So the question before us is simple. Will we treat the seabed as a shared inheritance, managed wisely and fairly, or will we allow short-sighted competition to threaten both equity and the environment? And so the ISA was created to answer that question.
Well, right now, you'd have to say with their lack of regulations, that they're encouraging the short-sighted competition.
Yes, agreed.
So, this advocates for them, but their track record, as I understand it, and I don't understand it, is that they've failed in their job.
Yeah.
For reasons that we don't know. And would you know what it is that's holding them up? I want to imagine it's something that is difficult to reconcile, like you're going to disturb the seafloor. How can you do that?
Well, and you're also dealing with a large number of nations with very different perspectives and interests, and yeah, and different access to technology as well.